Have you ever stopped to really think about AlphaZero? I mean, not just the headlines, but really stared at the concept.
Oh, yeah.
It's this AI that learned to play chess at a superhuman level, and it completely dismantled the best engines, the best players in history. But here's the kicker. It did it with zero human data.
And that's the part that always gets me. It didn't study grandmaster games.
Right.
It didn't analyze opening books. It was just given the rules of the game, how the knight moves, how to checkmate, and was basically told to play against itself.
And this leads us, it leads us right into this massive theoretical headache that I'm calling the AlphaZero paradox. Because according to classical information theory, I'm talking about the mathematical bedrock from Claude Shannon in the 40s, AlphaZero shouldn't be smart.
Right, because according to the old rules, technically it shouldn't have learned anything new at all.
Which sounds absurd to anyone who has seen it play. But that tension, that's what this deep dive is all about. We're looking at a really fascinating paper called From Entropy to Epiplexity, Rethinking Information for Computationally Bounded Intelligence.
It is a heavy title, I'll give you that, but the concept inside it's revolutionary. The authors basically argue that our old ways of measuring information, they're kind of broken.
Broken how?
Well, because they assume the observer is a god.
A god.
Yeah, or at least an entity with infinite computing power. If you have infinite time and, infinite brain power, AlphaZero's strategy is just the rules of chess. It's obvious.
But for us.
But for us, for humans, or even for AIs running on limited chips, it is not obvious at all. So we need a new metric, one that actually accounts for the fact that we all have limits.
Okay, let's unpack this then. We're on a mission today to understand this new metric, Epiplexity, and see how it supposedly solves three huge paradoxes in how we think about learning.
Let's do it.
So let's jump into the crash course. Who's the villain in this story?
The villain is unlimited compute. Or maybe more specifically, the assumption of it.
Sounds like a tech bro's dream, but explain why that's a villain here.
Okay, so in classical theory, specifically something called Kolmogorov complexity, we measure how complex something is by, the length of the shortest computer program you need to produce it.
Right.
Let's take a pseudo-random number generator, a PRNG.
Okay, so the code that picks a random song on my playlist.
Exactly. Now imagine a stream of numbers coming out of that generator. To a supercomputer with infinite time, our God observer, that stream isn't random at all.
Okay.
The supercomputer looks at it, reverses the math instantly, and says, oh, that's just a simple algorithm with a starting seed number of 1, 2, 3, 4, 5.
So for the supercomputer, that whole long string of numbers is just, it's boring, it's predictable.
Correct. It contains almost zero surprise, zero information, because the program to make it is so short. But now, imagine you or I, or, a laptop, looking at that same stream of numbers without having the key. To us, it looks like total noise. It's just chaos. It's basically indistinguishable from true randomness.
So we have this massive gap. The theory says simple, but our brains say random.
Precisely. And this is where the paper introduces two really key concepts to bridge that gap. We have to split information into two different buckets for us. Us, mere mortals.
Okay.
The first is time-bounded entropy.
And this is the noise bucket.
Yes. This is the stuff that looks like random noise to you, specifically because you don't have the brain power to decode it. It's that PRNG output when you don't have the key. You can't learn from it. You effectively just have to memorize it.
Okay, got it. And the second bucket, this is the one we really care about, I'm guessing.
This is the hero of our story, epiplexity, or epistemic complexity. This measures the structure, the patterns, the rules, the learnable logic that a computationally limited observer can actually pull out and, store in their weights.
So if time-bounded entropy is the noise that just goes right over my head, epiplexity is the knowledge I can actually learn and use to make predictions.
Exactly. It separates the useless noise from the learnable structure. And once you make that distinction, those paradoxes we mentioned, they just start to disappear.
All right, let's hit the first one. Paradox number one, creating information from nothing. This goes right back to the AlphaZero problem.
Right. So there's this strict rule in classical theory called the data processing inequality. It basically says you can't create new information just by crunching numbers. If you take a data set and process it deterministically, you can never end up with more info than you started with.
Which feels wrong, doesn't it? I mean, if I sit and think about a math problem where I analyze some situation, I definitely feel like I have more information at the end than when I started. I've connected the dots.
And this paper proves you're right. It uses this beautiful visual example called cellular automata.
Okay, so for everyone listening, Try to visualize a grid of squares. Some are black, some are white. And you just apply a simple rule to one row to decide what the next row down looks like. It's kind of like a digital organism evolving line by line.
And the authors, they compared 3 different rules or universes. So first you have Rule 15. It just creates this boring, repetitive pattern. Black, white, black, white.
Super low epiplexity. Nothing to learn there. It's obvious.
Then you have Rule 30. This one is actually famous in computer science. You apply these simple rules, but the result is it's just chaotic. It looks like snowy static on an old TV screen.
So using our new terms, this has high time-bounded entropy.
Exactly. It's incredibly hard to predict the next square, but has low epiplexity.
Why?
Because there's no strategy to learn. It's effectively random. You can't compress it into a smart rule. You just have to memorize the whole mess.
Okay, so where does the magic happen then?
Rule 54. This is the sweet spot. When you run Rule 54, it doesn't just make static. It creates these emergent structures, little geometric shapes that look like gliders or particles colliding and interacting with each other.
Wait, so just by running the program, just by doing the computation, we went from simple rules to these complex moving structures.
Exactly. The computation created epiplexity. An observer who's watching Rule 54 can learn, oh, that's a glider. If it hits that wall, it bounces. That is learnable structure that wasn't at all obvious in the initial rules.
So that solves the AlphaZero paradox. AlphaZero isn't just memorizing the rules of chess. By computing, by playing millions and millions of games, it's churning those simple rules into high epiplexity strategy. It's literally manufacturing structure.
That's the key takeaway here. Computation creates learnable structure. The information wasn't really there in a format we could use until the computation happened. It converts like potential info into kinetic info.
This is huge. It means thinking does create information. It explains why doing the work actually changes your brain.
And it leads us directly into the second paradox, which is all about challenging the idea that information is symmetric.
Right. Paradox number 2. Classical theory says information is symmetric. So predicting A and then B has the exact same amount of info as predicting B and then A.
Yeah, think about a book. Whether you read it front to back or back to front, the words on the page are the same. The bytes are identical.
But try reading a mystery novel backwards. It's a totally different experience.
And a totally different computational challenge. The paper uses this brilliant example from chess again to prove this point. They took a huge database of chess games, the Lichess dataset, and they trained AI models in 2 different directions.
Forward and reverse.
So scenario A is the forward way. You show the AI the opening moves, 1 point E4, E5, and you ask it to predict the final board state.
That seems, well, logical. It's just calculation. If you follow the instructions step by step, you get the final board.
Exactly. Computationally, it's pretty easy. It just requires simple calculation. Now, consider scenario B, the reverse way. You show the AI the final board state pieces are scattered everywhere, and you ask it to predict the moves that led to that position.
Whoa. Okay, that sounds infinitely harder. You have to be like Sherlock Holmes. Okay, why is the knight there? Well, it must have jumped from here to block that bishop.
Precisely. It requires deduction, understanding strategy, grasping the why of the game. You have to model the mind of the players. And here's where it gets really interesting.
I'm listening.
When they measured the epiplexity the amount of structure the model actually learned, the models that were trained on the reverse order had significantly higher epiplexity.
So because the task was harder, the AI was forced to get smarter.
Yes. The forward model just learned the mechanics. The reverse model had to build a deep internal representation of chess strategy just to solve the puzzle.
So information isn't just about the data itself. It's about the difficulty of the process you use to decode it.
That's the takeaway. If you want a smart model, give it a task that requires inverse thinking. Don't just ask it to predict the effect from the cause. Ask it to deduce the cause from the effect.
This is starting to make me rethink how I learn things. Maybe I should just read the answers first and then try to guess the questions.
It would certainly force your brain to build different connections. It forces you to construct a model rather than just, follow a path. And this connects beautifully to the third paradox, which is my personal favorite, the murder mystery.
I love this one. It starts with a quote from Ilya Sutskever, one of the godfathers of modern AI.
Right. He uses this analogy of a murder mystery book to explain the difference between generation and understanding. So the author of the book has a pretty easy job, computationally speaking.
How so? Writing a book is hard.
Well, creatively, yes, of course. But computationally, the author can just decide, the butler did it. They just write the name Butler on the last page, then they just write the rest of the book to fit that fact. It's a forward process.
Okay, I see your point. But the reader,
The reader has to read the whole book, connect all the clues, analyze the alibis, maintain this whole timeline in their head, and deduce that the butler did it. The reader is doing way, way more mental work than the writer did at that one specific decision point.
so the consumer of the data, is doing more computation than the creator of the data.
Exactly. And this just busts a huge myth in AI called distribution matching. It's this idea that a model can only ever be as smart as the data generating it. So, like, if the data comes from a simple program, the model can't be more complex than that program.
But the paper says that's nonsense.
They proved it with an experiment on induction. They created a data set using a really simple program that just masks some of the data. It just hides it. And to predict the missing data, the AI had to learn logic, specifically something called induction heads. That was actually more complex than the original program that made the data in the first place.
So the AI essentially outgrew its own creator.
In a sense, yes. Because the AI is a computationally bounded observer, it doesn't have the luxury of knowing the seed or the simple rule. It has to reverse engineer the logic from the outside. And that process of reverse engineering forces it to build internal structures, epiplexity, that are richer than the source material itself.
It's like, okay, if I watch a bird fly, the rule generating that flight is just physics and biology. The bird isn't doing calculus. But if I want to build a machine that flies, I have to embed aerodynamics and engines and materials science. My model of flight is huge and complex, even if the bird just does it.
That is a beautiful analogy. The generating process, the bird, is effortless. The learned model, aerodynamics, is incredibly high epiplexity.
So what does this all mean for the future of AI? I mean, we're spending billions training these things. Does Epiplexity tell us how to spend that money better?
It absolutely does, and it settles a massive debate in the field. Why does text data seem to make models smarter than image data?
Oh, this is the classic reading versus watching TV debate for AIs. We always assume images are richer, a picture's worth 1,000 words. Or...
In terms of raw bits on a hard drive, sure. Yeah. But in terms of epiplexity, no.
Why? Why is a picture of a cat dumber data than a text description of a cat?
Well, think about what the model has to do. If I give you a picture of a cat and ask you to predict the next pixel, what are you actually predicting?
I don't know. The specific shade of gray on a single hair, some random blade of grass in the background.
Exactly. And that is mostly time-bounded entropy. It's noise. Knowing the exact jagged edge of a leaf or the random texture on a wall doesn't teach you about the world. It doesn't generalize. It's hard to predict, but it's useless to learn.
Whereas text?
Text is dense with logic, with reasoning, argument. Because it rained, the ground is wet. When a model predicts the next word in a sentence, it's not just matching noise, it's following a thread of logic.
So text has high epiplexity. It forces the model to learn structure. Images have high entropy. They force the model to memorize noise.
Precisely. The paper introduces a way to measure this called frequential coding. It's basically about measuring the area under the loss curve.
Oh, slow down. Area under the loss curve. Let's translate that for the non-engineers.
Yeah.
Loss basically means surprise, right?
Yeah, that's a great way to put it. Imagine a graph. When a model starts learning, it's surprised by everything. Its error is high. As it learns, the error drops. If that error drops quickly and stays low, that means it found a pattern. It found structure.
And if the error just stays high?
It's just noise. It's randomness. The model stays surprised because there's nothing consistent to learn.
So high epiplexity means the model is constantly having these aha moments where the error plummets because it figured something out.
Yes. And the data shows that text provides way more of those aha moments per byte than images do. And this explains why a model trained on the internet on text can do math and code and reason, while a model trained on a billion images can. Well, I can mostly just identify cats.
It's not about the quantity of data. It's about the nutrition of the data. High epiplexity is like protein for the AI brain.
That's the big shift. We are moving away from measuring data by bytes, the Shannon era, to measuring it by learnable patterns, the Epiplexity era. Success in AI isn't just about the chick architecture anymore, it's about the diet. You need to consume high epiplexity data that forces the model to build complex internal structures.
This has been a wild ride. We've gone from AlphaZero to murder mysteries to the nutritional value of text.
It really reframes everything, doesn't it? It moves the focus from how much data do we have to how much struggle does this data force us to go through.
Before we go, I want to leave the listener with a thought that really struck me while reading this. The paper talks about representation learning, essentially being the accumulation of epiplexity. And our brains, we are computationally bounded observers. We can't process the whole universe at once.
Right, we have limits. We are defined by them.
So representational learning, what we call knowledge, is just the epiplexity we've managed to synthesize. Our personalities, our beliefs, our whole understanding of the world, are they just the compressed programs we've had to build because we can't see the source code of the universe?
That's profound. And it implies something else, too.
What's that?
If we had infinite brains,
Yeah.
if we were those supercomputers, would the world look boring? Would we just see the seed of the universe and say, oh, right, it's just a simple algorithm?
It makes you wonder. Maybe the richness of life, the mystery, the joy of discovery, maybe all of that only exists because we are limited, because we have to fight to understand it.
Meaning is a side effect of the struggle to compute.
I love that. Meaning is a side effect of the struggle. Thank you for diving deep with us today.
My pleasure.
And to you listening, next time you struggle to learn something new or you feel like you're reading the book of life backwards, don't be frustrated. You're just building epiplexity, and that is literally what makes you smart. We'll see you on the next deep dive.